part B, but I didn't talk about part A. So the part A, we have 9 concept questions. Quiz 5. So that's the quiz 5 part. All right. So quiz 5 equals part A of final exam. Quiz 5 mainly cover this module 5. This module, the current module. Okay. 9 questions. All right. So final. Remember, we have 9 times 4 plus 8 times 8 equals 100 points. All right. So there are 9 questions. Quiz 5, 9 questions. Okay. Concept questions from module 5. I plan to do this way. Remember, we did practice exercise questions before, right? Because our second half, we couldn't find time to do that. The first half we have time. We practice a lot. All right. So I just give the last exercise set question about this quiz 5. Okay. All concept questions. All concept questions. Okay. So I plan to give you 20 concept questions from module 5, for you to study. These 20 questions contain 9 quiz final questions. 9 of them are real final, questions. So this weekend I can make these 20 concept questions. So I can, I post it. So you practice for your study. So you study. You can start study part A a little earlier. So the purpose for this part, so you can start for part A a little earlier. Okay. Starting this weekend. Not at the final week. Too much work. Because the 9 concept questions are also important, right? So you also want to do well on part A. So we will do that this weekend. Total 20 concept questions. But I mark quiz 5 questions out. So when you study, so you know they are the final questions. Update. All right. Let's continue this topic. Minimum square error theorem. Let's estimate those, calculate those 2 integrals. And then we put together, the final result is this theorem. All right, so when we start, so that's the, 2 expressions we need to use. Little f, capital F. But the little f. All right. And E error. E, we know there are 3 terms. All right. The first, there are 3 integrals in this E formula. The first one, we calculate capital F square integral. Capital square integral. Then square here, we square multiply out. So it looks pretty complicated. Remember from the previous slide, by the orthogonality, we know all the cross terms are 0. All the cross terms are 0. So we only keep those terms, one function times itself. Those terms are non-zero. Okay? So that gives us pi, integral a0 times itself, non-zero. Okay? Then you take integral from negative pi to pi. So you get a pi times 2 capital A0 square. All right. For this term, only A sub n square cosine square, only this non-zero, you calculate its integral, yeah, it's A1 square, and so on. Yeah. So for each term, only this term multiplies itself. You take integral is non-zero. If this function multiplies other functions, you take integral all zero. That's the orthogonality property. Okay? That's the orthogonality property. All right. Yeah. So here we take advantage. Why orthogonality? So here, when you see all the square sum of, can you connect to another famous theorem? One famous theorem related to the square sum of squares. Can you really connect to that? Some theorem. One theorem, very famous. Yes, Pythagorean theorem. Pythagorean theorem. A squared plus b squared equals c squared. Here, this is c squared, f squared, and that big f squared. There, little a squared, but we have so many. Pythagorean theorem. Okay? That's the Pythagorean theorem. Pythagorean theorem, all the cross product, you take integral, all gone. You know, all gone. Yeah. All right. Yeah. So that's about that capital F. Yeah. Then another one. Little f times capital F. All right. So little f times capital F. All right. Yeah. Little f. All right. Yeah. Then, by the definition of the Fourier series, little a Fourier series, you know, we do integral, so you get these little a Fourier series representations. Yeah. Yeah. Okay. All right. Yeah. One by one. Yeah. One by one. So you just take little f times a0, take integral, you get this one. Little f, you put a little f here, you get a little a0 here, little, you know, everywhere. Okay? Yeah. So you get this expression. The third integral. Oh, so here, right. Yeah, yeah, because the third we do not calculate. The third is little f squared. Third we just keep as is. Okay? Third one we just keep as is. Yeah. But now add these two, you know, minus the second and the third. That's the E expression. This is the E expression. Okay? Yeah. All right. This E expression, other than the f squared term, look at these two brackets. These two brackets, we can, you know, so here, these two brackets, here. To look at these two brackets, let's look at this. We define another special E term. E star term, special one. The E star one, we replace capital 0 by little a0. Capital A by little a. Yeah, that's the E star one. Yeah. So that's the one we want to see when capital F equals little f. When capital F equals little f. Capital F equals little f. E is 0. E is 0. Capital F equals little f. Okay? Yeah. Or capital F capital F equals the partial sum of the little f. Okay? Partial sum of the little f. Yeah, because this is the partial sum of the little f. Yeah. So we get an E star expression. Yeah. All right. So the E star expression is one of the special cases, one special case in all E cases. A is E. This E expression is general because all capital A, capital B, you can choose freely. Yeah. Any number you can choose. Yeah. But when you choose capital A equals little a, capital B equals little b, that this E becomes E star. E star. Yeah. Here we want to show E star gives us the minimum error among all the E, all the possible E. E star gives us the minimum possible error. Okay? That's the goal. Yeah. To see that, we take subtraction E minus E star. E minus E star. You do subtraction. When you do subtraction, this little f squared term, the first integral, is gone. Okay? When you do subtraction, the first term is gone. Okay? All right. Yeah. Then the remaining term, yeah, when you do subtraction, yeah, you can make complete squares like that. Yeah. Yeah. So you can see the structure, the complete squares in that way. Yeah. Sum of complete squares, it's non-negative. Sum of complete squares, it's non-negative. Yeah. That's simple. Yeah. Property. Yeah. So we get E times E star always greater or equal to 0. So E always greater or equal to E star. That means our E star is the minimum error. Yeah, so that formula, this complete square formula, tells us E star error is the minimum error among all the candidates, yeah, all the trigonometric polynomials of degree n. It's minimum. Yeah. Okay? Yeah. So that's the, here tells us the partial sum of the Fourier series always gives us the best error. In what sense? Yeah. In the square error sense. The integral square error. That sense. It's the best. Yeah. If we use the supreme norm sense, it's not the best. Okay? We cannot say it gives us the best error in the sense of supreme error. Supreme error. Okay? The maximum definition of error. Yeah. These things here you will see in the concept questions. Okay? I talk about error. What error? Supreme error, square error. Right? Yeah. So you will see in the concept questions. Okay? Yeah. In what error it is the best? Yeah. I will say that. I make a statement, so you tell me true or false. So you need to know, here, the conclusion here. Yeah. All right. Oh, yeah. Jenny. Yeah. All right. Theorem, conclusion theorem. Okay, the square of f in 2. So yeah, that's 2 with fixed n. Yeah, capital F. This n must be fixed. Yeah, so then it's fair. Yeah, but we can make it very large. Then we fix it. Okay, all right. Relative to little f on the interval from pi to negative pi to pi is minimum if and only if the coefficients of capital F in 2 are the Fourier coefficients of f. This minimum value E star is given by 6. Yeah. Given by 6. Yeah. So let's say E star. Yeah. E star. Okay. Given by this. Yeah. All right. Yeah. Yeah. So this is our approximation. Fourier series approximation. Yeah. This result, basic result. Yeah. Next, Bessel's inequality and possible identity. Yeah. Possible identity. Bessel's inequality. Yeah. So that's the continuation from the previous slide. Minimum error. So we can derive these two formulas: Bessel's inequality, possible identity. Yeah. What's the meaning of that? We still we use the same notation as the previous slide. Same notation. Yeah. All right. And the E star representation we already have. Okay, now we know E star, so here, not E star, yeah, here, right, E star. We know E star greater or equal to 0, right? Yeah. Because E star is a special case of this formula. See? E star is a special case of that formula. Square integral always non-negative. Yeah. Because E star always great non-negative. There, so we have, we translate this E star greater or equal to 0 formula to this one. Okay? Yeah. Because here, we know E star is a special case of E. And from the E formula, we know E star is greater or equal to 0. So that we can translate to this formula. Yeah. So this formula is true for any given capital N, right? Any given capital N. And we can make that capital N very large. Can we make it go to infinity? We can make it go to infinity, right? If we make it go to infinity, is the identity still true? Oh, sorry, is the inequality still true? We make it that capital N goes to infinity. Because it's true for any N. Okay? Make it go to infinity, also true. Okay? So that inequality we call a Bessel's inequality. Yeah. So this is a Bessel's inequality. Make that capital N goes to infinity. Okay? Goes to infinity, less than or equal to this integral. Yeah. Bessel's inequality. Okay? All right. There. So first, this mathematician Bessel's discovered this inequality. Okay? Then another mathematician, possible, improve this result. So what's that? All right. So now, so let's consider this, trigonometric series. Okay. Yeah. All right. When we use trigonometric series to approximate, little f function, we know we use Fourier series. Okay. All right. Trigonometric system here. Trigonometric series represented, we use the trigonometric system to generate trigonometric series. Okay? And we call the system, right? Trigonometric system. Yeah. And remember, the first time when we talk about this trigonometric system, we call it basis, right? So this system forms a basis of all the trigonometric functions. All the trigonometric series, not functions. All the trigonometric series, it forms a basis of that. So what's the meaning of basis? Basis means we can use basis to represent all the functions in the space, right? Yeah. We have a function space. Yeah, here I use that term, function space. Yeah. A group of function, a space. Okay? Yeah. All right. In that space, so many functions, you can use the basis to represent all of them without missing anyone. No missing. Okay? Yeah, you can catch, otherwise you cannot call basis. If you have one special function you cannot represent, then this set of functions, you cannot call it a basis. Basis, you have to cover all the possible functions. Then you can call the basis. Okay? Yeah. Definitely linear independence. So two properties. First, must be linearly independent. Yeah. Linearly independent property. Second, you can represent all the functions. Yeah. So the second one we call a completeness property. Complete. Yeah, it's complete. So the second property here, we need to use the completeness property. Okay? So here, there is, Yeah, someone. Yeah, caption. Yeah, it's okay. Yeah. All right. Yeah. All right. So here. All right. Let me click it. I hope I do not cause any problem. Yeah. All right. So here, I'm talking about a property called completeness. Okay. Yeah. Yeah. These functions not missing anyone, representing all the trigonometric series. Yeah. Yeah. And certain function space. Yeah. Because here, I cannot talk about it. Yeah. So that function space. Yeah. Actually called square integrable function. Yeah. Square integrable function. Yeah. Here, let me. Derivative less than infinity. So these functions we call a square integrable function. So here, this trigonometric system is a basis for the square integrable function on that interval from -pi to pi. Yeah. So no missing. All right. So cover all of them, complete. Then based on that, okay, yeah, then this Bessel's inequality can be improved to the identity. It's a Parseval's identity. So by the completeness of the system. Yeah. All right. Yeah. So we have the Parseval's identity. Improve this. Okay. So how to improve? Goes to infinity. Then they are exactly the same. The difference is zero. Okay? Yeah? Yeah. Yeah. And this can be proved. This identity can be proved. But it's an improved result from that. Right? From Bessel's inequality, you don't know. Right? Yeah. Because you don't know if they are equal or not, right? You don't know if they are equal or not. Okay? Yeah. Could be unequal, right? Could be not equal. Yeah. But Parseval's identity tells us it cannot be non-equal. Okay? It must be equal. Yeah. Okay? All right. Yeah. Yeah. All right. Yeah. So that's these two, results. Yeah. Next, B.2, minimum square error for the sawtooth wave. Yeah, a special function called sawtooth function. Yeah. So let's look at that. Yeah. Definition of the sawtooth. Okay, tooth. Okay. All right. Sawtooth function. Periodic, 2pi periodic. Okay? Yeah. All right. Then let's consider, so the function given like this. Okay? Yeah. From -pi to pi, it's a linear function. Okay? Then 2pi periodic. Yeah. All right. So now we want to find a Fourier series of the sawtooth function. Yeah. Okay? Yeah. Just calculation by the formula. Observe, when we do calculation, here I use this example because look at the structure of the function. It has the special form. So what's the special form? F of x equals f1 plus f2. There are two. We split it. We split this function into two functions. F1 function, F2 function. Okay? Yeah. When we calculate the Fourier series, can we split into two Fourier series? Capital F, we calculate the Fourier series of F1 Fourier series of f2, can we calculate those two and adding together? Yeah. Yeah. All right. So f1 is x. f2 is a constant pi. Okay? Constant pi. All right. Then there is a theorem, simple theorem, sum and scalar multiple property of the Fourier series. It tells us the Fourier coefficients of a sum f1 plus f2 are the sums of the corresponding Fourier coefficients of little f1 and little f2. Yeah. We can calculate the Fourier coefficients for individual functions separately. Then we can add them up. Yeah? Yeah. Here, although simple, yeah, so natural, so simple property, but for this example, it's useful. Yeah. So we can, make our calculation simpler. Simpler. Okay? All right. Yeah. Because our f2, look at the f2 form. f2 equals pi. Can we say this pi is already a Fourier series of f2? Can we say that? The single term constant is already a Fourier series of function f2. Yeah? All the other terms, 0. That a0 term, little a0 term, is constant. Yeah? So it's already, this is already a Fourier series. Yeah? So we have its Fourier series. Now let's calculate the Fourier series of f1. Okay. But f1, is it odd function? Can you see it's an odd function? f1, it's an odd function. Okay? Yeah. Because f1, if you draw graph, f1, it's like this. Okay? f1 equals x. It's an odd function. Okay? f1 is an odd function. If f1 is an odd function, we know all the a coefficients are 0, right? Yeah? We don't need to calculate a coefficients. We only need to calculate the b coefficients. Okay? Yeah? So the f1, it's a Fourier series expansion is like this. Here. Before we calculate the b coefficients, we already know f1 should take this form. Yeah. So next, we only need to calculate b coefficients by the formulas. Okay? All right. Next, let's calculate the b coefficients for f1. All right. B coefficients, we just use the formula, Fourier coefficient formula. Yeah. Integral by parts, not too complicated here, hopefully. Yeah. All right. Yeah. So, yeah. That, that, and the answer. Okay? Answer like that. All right? Yeah. Cosine n pi. When n is even number, it's 1. When n is odd number, it's negative 1. So, positive 1, negative 1. Okay? So, that's that one. So then you have positive 1, negative 1. So your Fourier series of the original function, f2 Fourier series. This pi comes from f2, little f2. Okay? So you just put there. Then remaining from f1, that 2, yeah, because this b0, you always have that 2 over pi thing, right? All right. So, all right. Yeah. Yeah. So, yeah. Cancellation. Yeah. This pi can cancel out. Okay. 2 over pi. Yeah. All right. But n equals 0. This is negative. Negative. N equals 0. Yeah. Yeah. Sorry. N equals. Yeah. N cannot be 0, right? Yeah. Here. N cannot be 0, right? For b coefficients, n can only be from 1 to 3. N cannot be 0. Okay, for B coefficient. A coefficient, A can be 0. Yeah. So for B coefficients, yeah, because denominator n cannot be 0. Okay, so from 1, positive 1, so you have this, then negative 1, positive 1, negative 1. Okay, yeah. So you get a Fourier series of f function. Yeah. All right. Then we want to calculate E star. Yeah, because we want to calculate the minimum error for the sawtooth function. Minimum error for the sawtooth function. Yeah. Minimum error, sawtooth function. Okay? All right. And the Parsifal's identity. We can use the Parsifal's identity, right? All right. Yeah. So here. Minimum error for the sawtooth function. Here we use capital N. Capital N. All right? But we know when n goes to infinity, this error is 0, right? Yep. Parsifal's identity. When n goes to infinity, this error E star becomes 0, approaches 0. Okay? All right. Yeah. All right. So that's the partial sum approximation, like that. Partial sum approximation. Yeah. Better and better. Okay? Yeah. On one period. On one period approximation. Okay, all right. Then, now when n approaches to infinity, yeah, E star approaches to 0. Okay, yeah, E star approaches to 0. So then by Parsifal's identity, they're equal, right? Parsifal identity, we can equalize, So this pi thing, summation, but here we need to use n infinity. Replace n by infinity summation. This summation term, parenthesis pi equals this integral. This integral we can calculate, right? We can find its integral easily. Yeah. 8/3 pi cube. 8/3 pi cube. Okay? So this, summation times pi equals that one. Can we simplify it so we can get, this summation? Reciprocal of n squared. Summation of reciprocal of n squares equals pi squared over 6. Yeah. So that's another interesting formula. Non-trivial interesting formula. From seesaw, the seesaw function. We can find that. Okay? We can find that. All right? Yeah. So here, this topic, because our second Fourier analysis question, I want to find some question, with some interesting property. Yeah. Some candidates. I need to select. So which one looks better? Yeah. All right. Yeah. So so we finish this topic, minimal error topic. Yeah. Next is from Fourier series to Fourier integral. Yeah. Because eventually now, Fourier series, we have limitation. What limitation? Periodic function. We can only do Fourier series expansion on periodic function. If it's not periodic function, we cannot do it. That's one limitation. Another, the function is defined on a limited interval. It's not on the whole x-axis. Yeah. It's on a, interval, limited interval. Yeah. It's not on the whole axis. Yeah. These two limitations. Yeah. For some application problem, these two limitations not very good. So we want to overcome these two limitations. So the next step, we want to go to Fourier integral to overcome two limitations from the Fourier series. let me leave that topic next time. Okay, let me leave that topic next time. Yeah. So let's do our recovery session number 4.